So our next speaker is like Yoda in the engineering world. He's not 400 years old, but he's very well respected. Dr. Kelkar is the D.W. Reynolds Distinguished Professor, and he's the department chair of mechanical engineering. So if you want to study mechanical engineering, like Megan Smith said she did, he's the guy to talk to. He's at Clemson. You know, they were in the news for their football. He puts them in their news for their engineering. He's, I think, started 5 technology companies. He has a bunch of patents. He has a lot of graduate students. He's doing remarkable things. But in addition to doing his work, he's thinking how to help young people. And he has something to do with flight and Da Vinci. And he and his colleague, I think the CTO of one of his startups, are going to present for this block. And Dr. Atul, welcome, the Yoda of mechanical engineering.
Thank you, John. Can you all hear me? Just say thumbs up. Yeah, okay.
Yes.
Thank you very much, John, for that little inflated introduction of me. I'm really excited and also humbled with the speaker lineup that I had before me. So I feel honored to speak to you all. As John said, I'm a department chair at mechanical engineering at Clemson, and also founder of technology startups. The one that we are going to probably talk a little bit about is the educational software startup Parametric Studios products. And that my colleague, CTO of our Parametric Studio, Dr. Christopher Whitmer, he's with me today to help me share with you hopefully some interesting and exciting stuff. I mean, the excitement that I saw in all the previous talks, I don't know how anyone can top that. But amazing thing is just whatever we are going to present is kind of in line with that aerospace theme that we have seen in last few speakers. It has been really exciting presentation so far, and I'm sure you all have been studying physics and mathematics, which goes to the root of all the stuff you have seen. Now, what I'm going to say next is probably doesn't apply to this bunch of smart 9th graders which are on. I see from the questions you're asking, you probably don't need much of a motivation, and also with a teacher like Jen Spencer, I guess my next statement may not apply to you. But sometimes, you know, there are students across the world of your age, they wonder, where am I going to use this boring and difficult stuff in physics and math they're making me learn? And I don't blame those students as well, because I felt the same way at your age. So what Chris and I would like to do is to maybe change perception of those students, and maybe you know, you can help us help them by whatever you're going to see. So you know, physics essentially explains how things in universe work or behave the way they do, but engineering is exciting as it is all about doing. It is all about solving problems, like Megan said early on. We do that by analyzing things, designing, innovating, and building things that can help solve our society's problems. And what a great you know, thing to do to solve somebody's problems. Wouldn't it be nice if we can actually learn this art of problem solving while having lots of fun, like your generation I know has, playing video games, right? I know one thing about your generation is everybody is skillful at different things, but you all are skillful at playing video games. So why not use your skill set maybe to apply and learn science, and then you can actually do amazing things using those skills in science. And that is really the basic idea how got PSI started, right? So uh, Parametric Studio really builds innovative education software, and we do those through the media of engineering games, maker experiences, and product-based learning. So what's our passion? Our passion is to help students learn math and science through engineering by building the most effective and engaging learning tools and making awesome STEM games or kits and experiences. Uh, what is our research and what we make? We try to find out ways to use games to improve engineering in K through 12. Our products are engineering software, games, tools, challenges, and kits. And our beneficiaries are you, future scientists and engineers, right? And I'm going to have Christopher, who has been there from the foundation of this. He used to be my honor student back when he was undergraduate, and he's been with me throughout the journey. And even, I spent a large amount of my time with aerospace and with work with NASA. In fact, just for a second, I'm going to change my background here, um, to a collage of things I worked on just for NASA and the DoD and stuff. It goes from basic space antennas, hoop column antennas, all the way to Jupiter Icy Moons Orbiter, to recently the hypersonic program, and also the for DoD we just did the vertical tail problem of Joint Strike Fighter, and Christopher has worked on all of them with me. So he's going to now take you too deep into these games that hopefully can excite your friends and help learn STEM. Christopher, go ahead.
Hi, thanks for the introduction, Atul, and thank you. It's great to be here. Can you all see my screen?
Yes, we can.
Okay, that is great. That's the question of our times. So, engineering. Why engineering? Why engineering in K-12 really is what I'm saying. So I'm an engineer, so I'm biased, of course, but engineering is obviously about problem solving. And unlike a lot of other STEM disciplines, engineering is specifically about the practical application of science, technology, and math, and the betterment of the human condition, or at least it should be. You can kind of think of it as glue or duct tape, since we're budding engineers, that touches all of STEM and holds it together. Engineering and design methodology, specifically engineering design methodology, is kind of like the scientific method. It's like its cousin, in that it's a formal approach to solve problems. And so educationally, that helps you develop a way of thinking and solving problems in everyday life. It helps you build connections and skills and knowledge to all of the other STEM disciplines and build confidence in those. And it helps you to sort of work in teams. So engineering is a team sport. The goal isn't really to make all students engineers when you're presenting engineering to kids like you, or maybe not like you, but just in general, K-12 education. The goal isn't really to make everybody an engineer. The goal is to teach everybody a problem-solving mindset. And in that way, engineering is just awesome at that. But again, I might be biased. There's a few things with engineering K-12 though that when we started doing this and building games and all kinds of things like that, that we ran into noticing how it was instructed, and has a lot to do with time and the amount of time you have available, as well as budget and all that kind of stuff, to do really interesting things in your classes. And so a lot of times the really great things that connect the other STEM disciplines to engineering get forgotten. So using games for engineering, why would you want to use games? Well, a traditional approach to engineering in the classroom would be to conceptualize something. Probably you're presented with a problem ahead of time. You don't necessarily formulate it yourself. You may not even formulate the objectives and constraints, so the problem might be fully defined. And that's a time-saving thing usually, just for instruction. But you conceptualize it, you analyze it, you build a prototype, you test it. You all have probably done this a lot in your classes, and it's a traditional way that K-12 engineering is done. And if your class budget and project times are enough, you might even get to see it through. A lot of times, you don't get a lot of time to iterate and things like that. Maybe it'll work, maybe it won't. Either way, you're probably not able to fully explain it. And you probably did not have to use a lot of math and science to describe it. And most certainly, you didn't get a lot of time to iterate on it. And iteration and exploration and trying things and failing is really where you learn a lot. And so this is kind of a recipe for misconception and frustration. Although it's a good start, you're doing engineering at least, and you're learning a lot of things that way. But maybe there's a better way. And so we set about trying to add sort of gamification to engineering when it's instructed at K-12. And that's, in this sort of approach, what you do is you still develop concepts, but they're digital and parametric. And you use math and science ideas to describe the systems and subsystems of your operations. So you're you really have to make a lot of connections to STEM. What that means is developing an equation, maybe you're utilizing data analysis techniques, maybe you're building a computational article that you're going to use. But in that process, you are building up the fundamental description of your design methodology, all the way from specifying objectives and constraints to, you know, the end result of modifying a parametric geometry. So once you do that, you can gamify the analysis and simulation, and you can digitally iterate and optimize. So the real advantage of doing something like this, besides it being fun and gamified and making a lot of the things that maybe wouldn't necessarily be engaging and fun, is that you can save a lot of time. So I can do 100 iterations of a properly set up digital design problem. Then I could do in the time that I would make one glider, right? So if I'm talking about gliders in this case. And then once you have that ability to do numerous iterations, try, fail, you can really understand the fundamental phenomena that are driving your design process and the things that you're connecting to, be it atmospheric model, or maybe you're looking at different descriptions of material strength or whatever. But you can really get into it in a way you can't do when you're just doing basically a design test build sort of strategy. So the benefits are, it makes it really engaging. So, and it makes it engaging to a wider audience. Again, Atul mentioned, you guys may not be having a problem being motivated to begin with, but a lot of kids are not motivated by math and science. And so anything you can do to engage them and show them, demystify it, is a great thing. And so it's faster, of course. It lets you really start examining and understanding the impacts of your choices, your phenomena, your methods. It makes failure a good thing, if that makes sense. You fail fast and you fail fun, because if you fail here, it's a game. Obviously, it's there's always something that happens. That's one of the objectives when we design anything in any of our games that are engineering based, is we make the failure mode extremely enjoyable, so that you're encouraged to fail. And that sounds strange, but that's actually where you learn the most. So, and then ultimately, this all leads to better design. It means you get a deeper understanding of everything driving it, and it's a better learning experience. And of course, it's a team sport, so a lot of games are just set up for that to begin with. It's kind of a strange thing. You're both self-motivated and can be sort of a self-starter, but at the same time, you have to share with your peers what you're learning, and so it can be simultaneously a great individual and team exercise. So this is the kind of STEM that we use in our projects. I mean, it varies all over the place, from science and math concepts like physics, the learning sciences, which you may not think about, because if you're building an education game, there's a lot of psychology and how people learn and visualize and understand and ideate. There are math concepts, of course, anything from linear algebra to calculus, and there's a lot of calculus. Hopefully I'm not hearing any groans out there. So, but and then other things you may not think about, you know, like animation, drawing, and painting. That's maybe not as typical in a lot of engineering projects, but in our engineering projects, it's really central. It's a big part of what we do. And then, of course, there's the engineering, which is the duct tape or glue, if you will, that sort of brings all this stuff together. And I didn't know how much time we would have. So what I wanted to do was to first kind of walk you through an example of what some sort of stuff is that we do and what it looks like in practice. And so I'm going to switch my view here, hopefully. All right, so this is DaVinci Flight. It's just a little bit about it. It's set up to be sort of a futuristic design game. You're in a lab, or a design lab, or a series of them, and you're told not told a lot about the world, but your goal is sort of to explore it, and you can explore it from the air. And so basically the premise is you're designing different kinds of sort of hobby scale drone size, UAV size vehicles. And then there's a lot of other things that go about this than just this game, and which you'll see really soon. So I'm going to launch it. Can everybody see this, by the way, before I keep going?
I only see one slide. Can you switch to another slide?
Yeah.
Yeah, you may need to put it in presentation mode.
Yeah, it's not interactive. We don't see
Okay.
you interacting.
Okay.
Yeah,
Let's do
go to
this.
presentation mode.
Whoops. Let me change with the.
Luke Skywalker, I think you, yeah.
I'm trying. There we go. Is that
Okay.
doing it now?
Yeah.
We just see black. Switch screens.
Yeah, it
Yep.
is okay. It's on now.
Okay, good. So yeah, I had it in 2 different windows. It didn't launch from the PowerPoint.
Okay.
So anyway, so this is the futuristic sort of design game, and there are different things inside of it where you can kind of wander around physically, walking around the lab and so on. And that's fun to do. But there are different sort of rooms in here that are sort of mission oriented, mission planning oriented. There's inventory stuff for kinds of things you can put inside your game. There's a display case for achievement and library docs and stuff like that. And then there's concept creation and analysis and simulation tools. And so I'm going to show you a really quick. So the kinds of missions you can do, they really vary quite a bit. They can be more science and math oriented, like teaching a particular concept, maybe simultaneous solutions of equations, or perhaps forces and moments or something like that. But they're also sort of design oriented. And I've got one selected right now, which is a design of a glider. So we'll kind of go through that one. You can
So in
also
the
go around to
interest
the
of
various.
time, Christopher, the time, keep eye on the time. Yeah.
Yep, I'm about done here. So, so the cool thing is that you would maybe start to think about design process. I've kind of skipped the first part of this, which is putting together geometry, but that's actually okay because putting together geometry is sort of what everybody thinks about when they're thinking about what a design is. But really, one of the more important things is building up the models that describe your design, and at least if you're doing a digital design that you want to do optimization on. And so I'm going to show you kind of what that looks like in our design room. And this is sort of the central idea behind what we're trying to do. So in our games, we put together these, you can kind of see a super complicated block diagram. We put together these sort of systems that describe various aspects from the objective down to the various fundamental things that define all the variables and forces and stuff in that objective. So you can see some things in here that relate to physics, of course. There's an aerodynamics forces solver, there's a mass model, there are models for how the motions of the elevators and ailerons and rudders affect things. There's variables having to do with the state of the aircraft. Those are sort of directly related to Newton's laws, of course. And then there are all kinds of vehicle parameters that you can change. And so in all that, you can sort of modify a design and sort of build it and design it and change it. And there's a lot of flexibility of things you can do. So that's one of the things that you can do. Okay, another thing that you can do is, of course, simulate it. So, and that's a key part of the gamification as well. So give me a second. All right, good. It's cooperating. So every design you can simulate, even if it works or doesn't work. And the whole point of it is you want to fail, and you want to fail in a way that's like catastrophically fun, if that makes sense. And so the simulator is more like a drone view. You can kind of adjust things. All the changes you make to your design are immediately reflected and then brought into this. But this particular simulation has been designed such that it has a pretty good replication of reality, at least for this size and class of vehicle. And so that way, you get a pretty good feel for whether or not it would work in reality. And so you can kind of see there's some objectives in this one where I'm supposed to be exploring and flying through various things and so on and so forth. So let me get out of here. And then the last thing you can do or not the last thing, but one of the last things that you can do once you have a good design is to export things and to sort of make them and 3D print them. And all of our games are sort of set up this way, where you can basically lay out a structure that can be made. This one's a 3D printable one, but you can also lay them out such that you're going to do them with laser cutters and various things like that, and then export them. And I'm going to quickly jump out of here and show you what that looks like. And I'm going to, sorry, I have too many things in too many places. And so let me, whoops, there it is. And this is kind of like, once you end up with a design, can you all see my screen?
Yep.
Once you end up with a design, you can begin sort of 3D printing it. And there I'm making parts of the wing. You can kind of see, I just did this last week. You can assemble it. You got a pretty good, decent glider design. It's a little on the heavy side. And then you can test it. So that's kind of the whole process. But then instead of that being like the only thing that you get time to do, you would have had time to like really optimize it, really understand what's driving it, and so on.
Hey, Chris, can I just jump in for time? I think this is remarkable. Students, you're hearing from two people who are building a tool to help complement what goes on in the classroom, and maybe could be a tool in the classroom. And I wanted to put personalities behind this, and thanks for perpetuating the quest for flight. This is great. And behind me, I have some bread that was baked by some MIT students who are exploring the properties of bread. Corey, can you reveal yourself for a second? And then Kartish is up next. And Megan Smith, I look forward to you connecting with that team and giving them some ideas and some thoughts on how they could help serve young people. So Corey is the Michael Jordan or the Biles, the gymnast. He's an amazing world-class accordion player. He's won the world's four times or 5 times in the accordion, and he's going to honor Kartish, who's coming up next. He's played at the White House. He's played around the world. Ladies and gentlemen, Corey.
Thank you, John. And Christopher, I got to say, as being a video game guy, I want to play that game now and learn my physics through building something. That's incredible. You guys are lucky to have something like that. All right. So, yeah, I will play a little bit of accordion, but not what you would expect. This is it's an electric accordion. So I'll play a little medley of stuff here on an electric accordion.
Hey, thank you, Corey, and Corey will be doing the musical interludes between our final four speakers. Next up is Kartith. This could be one of the most important talks of tonight or today. He went to Caltech. He's a professor at MIT in chemical engineering, and he has an idea of what we could be doing with plastics. And it's really important for those who are interested in the green economy and trying to prevent climate Armageddon. After him, we have Kayun, who's in from London. I see she's in the Zoom right now. She's at the forefront of cybersecurity. There's going to be a lot of need for minds in the cloud, and she has some interesting things that she can't wait to share with you. And then we have Don, who wrote the programming for 52 years ago for the Apollo landers to land on the moon. And he went to BU and worked in Draper's lab and created the software that allowed us to land. Neil Armstrong, as Mike Collins, who passed away just a few days ago, circumnavigated the moon. It was his programming that helped us get us there. And he has a lot of things to say about that. And then finally, we have a student, the youngest presenter, Julian, who is who rose crew at MIT, who's just a few months older than all of you, who can't wait to share. He's going to close us out. So ladies and gentlemen,